Hello everyone, welcome to this additional topic on common derivatives. So I just want to use this additional video to highlight a few things on when we should take good derivatives and what rules should we use. Now, first, the constant function is going to be always a flat line. So the flat line is going to be having a slope of 0. So that's why the constant function is 0. However, when the function becomes more complex, then we need to use different rules depending on what function it is. So the power function itself, we treat x as a variable, right? That's our identifier, and then n now is a constant. So n is a constant. So example is like x to the power of 2, and then we take the derivative. It's going to be 2x. So let's just review the basics first before we move on. So when we see a function y, we usually mean that it's a function of x. We express it as a function of x. So f is a function of x. And when we want to take the derivative, we usually mean that we want to take the derivative of y with respect to x. So what do we mean by that? So take the derivative of y with respect to x. So this is one way to write to denote the differentiation operation. Now we can also write it as d over dx, and then the functions of f of x. So this is another way to write it, which means we're going to take the derivative, right? And we can also say this is y prime, right? So this is prime, right? So this special thing is prime, and this is also equal to f prime of x. So this is just different notations to express the same thing. So exponential function itself stays, but more general form is when the base is anything. So basis now is a constant, x is a variable. So we just plug in, and then we have an additional term here. Of course, when b is equal to e, right, and we have ln e multiply e to the power of x, which is going to be e to the power of x, because this is going to be just 1. All right, so similarly, we have the ln x is going to be the inverse of x. So more general form is this one, and we just need to multiply this actual term in the denominator. And again, when b equals to e, we can recover the special case. All right, so that's about it. And we also have a few rules when taking derivatives. This is where I want to highlight a bit. So first, we have the product rule. So meaning we have two functions, u and v, right? U is a function of x, and v is a function of x. When they multiply with each other, right? So we can have derivative. Then the derivative is going to be first we take the first one and then multiply the second one, take the derivative of the first one, and then we switch the sequence. So that's going to be u itself, right? So this is called the product rule. And we also have the chain rule. So which is going to be if we have a function u, and then inside it we also have another function v, right? So we'll take the derivative. So basically, when x comes in, we go to v first, and then go to u as a function transformation. And then when that happens, we need to take the derivative of the outer layer first, right? So the inside stays as the same as the entity, and then we take the inside, the derivative, right? So this is like a sequence of transformations. So x goes through v and then goes through u, right? So that's the forward operation. Then we take the derivative, then we say we take the u first, then we take the v derivative, and then multiply together. So this is how it gets the derivative. For the quotient rule, right? So quotient is ux over vx. So this is also again gonna multiply, gonna plug in this formula. So we have what's happening for the bottom is that we have the squared function of v, and then we take the derivative of the first function first, right? And then multiply b, and then this is a minus, right? It's not a plus. So we have the ux v prime x. So this is the different rules, 3 common rules. Now, how do you remember which one to use? So actually, all the rules are exchangeable, right? So no matter what rule you use, you're gonna always recover the same thing. So what I mean by that? Let's look at one example. So x to the power of 6, right? So if we use this and then use the power rule, we can easily get 6 multiply x to the power of 5, right? So this is the product rule. And let's give us a challenge. So what if we want to use the product rule and express it as x squared and x fourth, right? So this is the same thing. And so we want to use the product rule to calculate it, right? So use the product rule. How do you calculate? So first we need to calculate the first term, and then we calculate the second term. So, and that's going to give us 2x multiply x fourth and x squared multiply 4 times x cubed, right? So we just multiply it out, and then we have x to the power 5, and that gives us 6 x5, right? So it's gonna the same thing. So let's check. Now let's look at the chain rule, right? So we express a chain rule. So what is a chain rule? Now let me express as x to the power of 2, then to the power of 3, right? So this is the same thing as x to the power of 6. We just take the derivative of this term, right? So how do you get it? Now what happens is that x, when it comes in, I'm gonna go through the squaring effect first. So first I express it as a composite function. So that's the composition. So we get x squared first, then we get the raised to the third power, right? So this is the second operation. Now let's go backwards. So we're now going to take the derivative of the outer function. So which is that the outer function is just anything comes inside raised to the power of 3, right? So anything that comes falls into the square, just raised to the power of 3. So you're gonna take the derivative, right? It's gonna be 3 anything to the power of 2, right? So this anything now is x squared, right? So I'm just saying that okay, so now the derivative is going to be 3 to the power of 2, right? So we can just express this now, which is equivalent to 3 x fourth, right? This is the first one. Second one, it's simple to get, so 2x. Now I just have 2 terms. So it's going to be 2x multiply 3x to the power of 4, which gives me 6 to the power of 5. Which is the same answer. So any answer we get, it should be the same as earlier, right? The first one. Okay. So that's the chain rule. And if you are if you becomes proficient, more and more proficient in chain rule, you can just write it out directly. So you can just say, oh, outer function gives me 3 to the power of 2, right? And this is the outer function. Then let's zoom in the inner function, right? So now this inner function gives me, again, let me write it out, 2x, right? I can just say, oh, it's now x power 5. So outer function, inner function, write it down sequentially, right? Sequentially. So, okay, so now let's look at the last one, which is gonna be the quotient rule. So quotient rule, we can express it as x power of 8 divided by x power of 2, right? Same expression. So what we have here is going to be a long sequence where we have the x power of 2 squared first. Then we have x power to the power of 8 derivative multiply x squared minus x squared now derivative, and then x to the power of 8. All right. So what we have here is 8x 7th power x squared, and then 2x multiply x to the power of 8. Then we have x to the power of 4. So we just plug in right? To the power of 9 minus 2 to the power of 9. The bottom stays. So we have here. I'm just writing out the expressions, combine them together, and we have 6, 12, 5, which also we're gonna check, right? So this is how we can show that no matter what rule we use, they should ideally you would expect them to give you the same thing. So so there's multiple ways to get the same answer, right? And so that's about this one. And I want to use another example to show that so we can actually use different rules together when solving one problem. So for example, when we have f of x equals to x to the power of x, right? And this, in this case, we need to assume that x is positive, right? So what do we do about this? So what do we do about how to get the f prime of x, right? So this is the question. Now, remember that this is not a power function because power function is to say x to the power of something, right? This something needs to be constant, and it's not an exponential function because the exponential function, the bottom base needs to be constant, but now the base is also a variable, right? So that means that we cannot use any of the rule. So what do we do? Now, our sort of first intuition is that this x that lives in the exponent space is something that's gonna be troublesome to work with. So that's why I want to move it down, right? So how to move it down? One technique is to say that let me just raise it to the power of e, and then we have the ln itself, right? So why can we do that? Because x is equal to e to the power of ln x, right? This is a rule we covered earlier. And so that's how we can do this. So we have, now we can bring it down because now we have the ln function here. So x to the power of ln x. So this one stays. So still taking the derivative, right? So now at this step, we can think about using the chain rule, right? Because now x goes self-transformation and then finally raised to the power gets exponentiated. So so let's use the chain rule. This is one of the ways we can do. One of the things we can do. So first, they just write it out itself. This is outer layer, right? Outer layer derivative, which is itself, because this is essentially e to the power of something. Which the derivative is going to be still e to the power of something, right? So this is based on the derivative rule. Next, we have x ln x derivative, right? So how do we go about it? So this is where we can use the other rule, which is to treat it as a product, right? And then if we treat it as a product, then we have first take the derivative of x, then multiply ln x, then plus x multiply ln x derivative. So this is 2 terms. Let me just write it out. So in this case, we have just ln x because x derivative is just 1. And we have this can be so this can be x multiplied by 1 over x, which is going to be 1, right? So we're just going to add 1, and yeah, that's our answer here. So if we write it back, because this one is still can be something we can convert back to the original form, right? If we just move x back, then we have x to the power of x, then 1 plus ln x, right? So this is the final answer. Now, this is one way to do this. Another way is to use implicit differentiation. So so if we say now we express y as x to the power of x, so why we switch to y? Because we are now thinking of taking ln for both sides, so that we can use we can take the ln we can use the logarithm transformation. So if we use it, then we have ln y equals to ln x to the power of x, which can give us x ln x, right? So now we can take a derivative of both sides. So which means that take derivative of the left side and take derivative of the right side, right? And then you can continue to expand in both sides. So the first side is going to be 1 over y. Why? Because now it's a Laurent function, right? So it's 1 over y. But we need to remember that y is also a function of x. So y should take the derivative with respect to x as well. The right side is something we did earlier. So just gonna be 1 plus Laurent x. Okay, so what we have here is now y prime, which is the derivative of y with respect to x, is gonna be y multiply 1 plus Laurent x. And then we just plug in the definition of y, which gives me the same answer as earlier, right? So we just plug in. All right, so that's just two ways. And in this case, we have used the different rules, the chain rule, the implicit differentiation, and also the Poisson rule, right? Which to be the more neat compared with the first one. Okay, that's it for this additional video, and thanks for watching.